I welcome all my students to the course on mechanics of materials, and this will be our second course on mechanics of materials. Um, I'm from the Department of Mechanical Engineering, University of Kashmir. As far as the outline is concerned, the course outline is concerned, we are going to start our course with the transverse shear in beams. But before we understand the concept of transverse shear in beams, it's very important for us to have a quick revision of what students are usually taught in earlier course of mechanics of materials. And in order to understand the concept of transverse shear in beams, we need to have a good understanding of the normal stresses in the beams. As far as the concept of normal stresses in beams is concerned, let's suppose that we have a beam. And this beam is a simply supported beam having a pin support at one end and a roller support at another end. And this beam is having a sort of distribution and a sort of a load is on it. The load may be a concentrated load. The load may be in the form of a distributed load having intensity W as a function of X, or it may be having, say, for example, some moment acting at any point on its span. Suppose that moment is M naught. Because of the distribution of the load on the beam is subjected to strains. The normal strains are created on the beam. And as far as the distribution of normal stresses is concerned, the distribution of normal stresses is linear at any cross section of the beam. And this normal strain variation is usually measured from an axis, what is actually called the neutral axis. The formula that governs the distribution of the normal strain across at any area of cross section of a beam is the formula for strain, that strain is equal minus y by c strain max. An analogy to the strain formula, we have the stress formula. The strain is zero at the neutral axis. The neutral axis is the axis which it's actually the projection of the neutral plane, the plane which neither undergoes expansion, nor undergoes compression. It's neither in tension nor in compression, because we know as the beam is subjected to the load, the upper portion of the beam is under compression and the lower portion of the beam is in tension. So the lower portion of the beam is the portion which usually expands, and the upper portion is a portion which undergoes compression. Now, if you look at this distribution, the normal stress distribution, the normal strain distribution, the strain is maximum at any cross section of the beam. The strain is maximum at the top surface. At the top plane, the strain is maximum and it's zero at the neutral axis. And as we move, the distribution is reverse above and below the neutral axis. Above the neutral axis, the strain is compressive, and below the neutral axis, the strain is tensile in nature, which we know. In fact, this concept is derived from the assumption that the beam is subjected to pure bending. It only has, bending moment above it. There is no load about it, but it's applicable to other sorts of loading distributions as well. Now, the formula, what is actually known as the Flexural Formula, which governs or gives us the normal stress distribution at any cross section of the beam, is sigma is equal minus y by c sigma max, which says that again at the neutral axis, because we are measuring every distance. We already know from the earlier courses on mechanics of materials that all the distances are to be measured from the neutral axis. And say, for example, the neutral, an axis which is perpendicular to the neutral axis, let's suppose that's an y-axis, okay? So at the neutral axis, the stress is zero. And as we go above the neutral axis, the value of y is positive because we are treating y to be an axis which is perpendicular to our neutral axis. So y is positive. Therefore, stress is compressive, it's negative, and c is the radius of this, it's the maximum distance to the surface measured from the neutral axis. Okay. So y by c into sigma max. So at the neutral axis, the stress is zero. Above the neutral axis, the stress is compressive, and below the neutral axis, the stress is tensile. And sigma varies with y with big, so sigma being the linear function of y. That's why it has been drawn in the form of, the distribution is essentially in the form of the straight lines which are drawn here. Now, this formula is called the Flexural Formula. Uh, in fact, it's express it in terms of the bending moment as sigma is equal to minus my divided by I, where I is the moment of inertia of the area of cross section about the neutral axis. So what I mean to say is this formula is also written as the sigma is equal to, which we already know from basic mechanics, it's equal to minus y my divided by I. It's like this. So as far as the m is concerned, m is the bending moment at the point, at the area of cross section where we are measuring this stress. And as far as y is concerned, it is a distance measured from the neutral axis along an axis which is perpendicular to the neutral axis. And I is the moment of inertia of this area of cross section about the neutral axis. Okay, the projection of neutral axis here in fact will be in the form of a point. Okay, if we, okay, so this formula is what is in text called as the Flexural Formula. Okay, so this formula gives us the values of the normal stresses at any cross section of the beam. Okay, so we already are familiar with this formula, that how we calculate the normal stresses at any cross section of the beam with the help of these types of formula. So we all already familiar that at any cross section of the beam we do have the normal stresses. Okay, now the normal stress distribution at any cross section of the beam is like this. Okay, so this z axis is our neutral axis, whose projection I was telling you is in the form of a point, because this was the view we were taking. So this neutral axis will be in the form of a point, but this is how the neutral axis in the side view or in the front view looks. Okay, so whatever stresses are measured above the neutral axis, the stresses are compressive, and these are like this in a direction which are perpendicular to the area of cross section. And below the neutral axis, these stresses are, tensile, and again in a direction which are perpendicular to this area of cross section. That's why we are calling these as normal stresses. The stresses, normal stresses, are those stresses which exist, or uh, uh, which exist, which are exerted, which are present on an area in a direction perpendicular to it. Okay, so that's why we call them as the normal stresses. So this is the direction of normal stresses. This is how the normal stresses behave above the neutral axis, and this is how the normal stresses behave below this neutral axis. Okay, now if we take a small element out here, that's what has been projected out. A small element has been taken out. Then on this element we have the normal stress acting, that is sigma. For the equilibrium, there must be sigma acting in this direction as well, because this element is under equilibrium. If we have uh, the normal stresses, which the formula for them is sigma is equal to minus my divided by I. Okay, so if we move from this position to this position, the bending moment, if the bending moment does not change appreciably, then the value of sigma on this side has to be equal to the value of sigma on this side. Okay, so this is how these normal stresses actually behave. The normal stresses are given by the formula is equal to minus my by I. So this is what is usually taught in the basic mechanical courses, basic mechanics courses to the students, how we calculate these normal stresses acting at any cross section of the beam. Okay, now what we have to discuss in this chapter, we have to start with what we call as a transverse shear. Our journey begins with the transverse shear. So as far as the transverse shear is concerned, the transverse shear will be now starting with, we will be starting this concept of transverse shear from our textbook, which is the Fundamentals of Mechanics of Materials by R.C. Hibla, and the transverse shear will be beginning in the coming class. Thank you.